The clapper from the 1980s was a sound-activated electrical switch that let users control household appliances, like lamps, TVs, or radios, just by clapping their hands. It worked by being plugged into a wall outlet, where an appliance, like a lamp, could be plugged into it. A microphone inside the clapper detected sharp, distinct sounds, like two successive claps. A simple circuit then interpreted the clap pattern and toggled power to the connected device accordingly. To see a visual demonstration, let's look at the TV commercial that popularized the clapper.
Honey, turn off the light.
Has this ever happened to you? Presenting the Clapper. Lets your appliances turn on and off just by clapping. Clap on the music. It's easy. Just plug the Clapper into any household outlet, then plug in your lamp, TV, or stereo.
Clap on, clap off.
For places hard to reach, the Clapper makes it easy. Plus, the Clapper comes with an extra feature to make your home more secure. Turn to the Away function, and your lights turn on at the first sound it hears. Minutes later, they turn off. And the Clapper resets to help protect your home. Leave your appliances plugged into the Clapper, and your lights will go on, turning away unwanted guests.
Clap on, clap off. The Clapper.
Now, based on this antiquated commercial, our lab team prototyped a modern version of the clapper using two breadboards, an electret microphone, an op-amp, a few BJTs and MOSFETs, and a couple resistors. We also used a few lab instruments like an oscilloscope, waveform generator, and power supply to test and show the functionality of the subcircuits. We built several subcircuits during the duration of our experiment, each of which that handled various specific functionalities that were present within the original clapper. We decided that, in order for our breadboard prototype to replicate the functionality of the original clapper, it needed to do the following. First, it needed to register a loud clap. So small sounds should not trigger the LED to turn on or off. Next, we need to have an LED turn on and remain on long after a clap has been registered. And finally, the LED should only turn off when another loud clap is heard. So while we were brainstorming, we came up with 4 modules that represented sub-circuit functionalities that needed to be addressed by our circuit. The BJT latch, the microphone, the amplifier, and the comparator. The BJT latch. The need for the BJT latch arose from a need for memory. Once a piece of information is latched into a state, on or off, in the latch, it stays in that state until it's explicitly changed by an input signal. This makes it perfect for applications in the clapper circuit where we want to remember whether the LED should stay on or off after a clap. The electret microphone. An electret microphone is a type of condenser microphone that is widely used in everyday electronics, like smartphones, laptops, voice recorders, and sound-activated circuits. It's small, cheap, and sensitive, and it converts sound waves, or pressure, into electrical signals using the capacitor principle. It has one downside though: the signals it outputs are too small and need to be amplified. The op-amp, which is where the op-amp or operational amplifier comes in. An op-amp compares two input voltages, the inverting minus and non-inverting plus terminals, and amplifies the difference between them. We can take the microphone output and amplify it to a useful voltage. The amplification level of the op-amp is decided by a resistor ratio in the op-amp circuit. The comparator. A comparator is an IC, or integrated circuit, that compares two input voltages and outputs a digital signal based on which input is higher. Ideally, we would have used this to compare our microphone voltage with a variable voltage threshold we would have created with a potentiometer resistor voltage divider combo, but this did not end up working out. The circuit got complicated and we gave up on debugging it. In the finished product, we use a single MOSFET instead of this subcircuit, simplifying, albeit sacrificing some features, the circuit. The following is a documentary of how we built and tested each of these subcircuits.
Here's our BJT circuit we're using to keep the light on whenever we get the impulse and turn it off. So when it's connected once, it turns on, and when it's connected again, it turns off, like that. It's on this part of the board, and these two wires represent our button right now. We're just connecting them to make it easier to see. And we have the schematic over here. So how the BJT circuit works is this is a transistor that controls if the light's on, because when this has current, the light has a path to ground and will turn on. And how it stays on is when this transistor is on, current's flowing through here. This makes this a lower voltage than 9 volts, because when this isn't connected, it'll be 9 volts because there's no way out. When it's not connected, it'll be lower than 9 volts. This means that this transistor will no longer be activated, which in turn means that this no longer is a path to ground. So instead of going to ground, this will stay at 9 volts and it'll turn on this transistor. And when this transistor is on, the 9 volts can go and activate this transistor. So pretty much the button initially turns on this transistor, and then it will keep itself on due to these series of transistors. How our setup turns itself off is that when this area is on due to this transistor line current, it'll also turn this transistor on, which will connect the 9 volts to ground, and it'll also connect this capacitor to ground, because the shortest loop is to ground, not to power and whatever. But this means the capacitor will be at 0 volts. That means next time we connect this button, this capacitor will keep this area at low voltage, because the fastest path for the 9 volts coming through here will be through here through the capacitor to ground. This means this transistor stops and turns off, which goes around the loop and then turns this off, meaning everything will be off again. And just to be sure, including since this is all off now, this transistor won't have this transistor won't be powered, so this connection won't be to ground, meaning this capacitor will charge again and it'll be able to turn on again. So it can turn off and on multiple times. And here we have, as you can see, we have the positive probe, the oscilloscope connected to one side of the capacitor, and the other side is connected to ground right now. So if we look at the oscilloscope, here's me connecting them. You can see the voltage goes up. This means, or you can see the voltage oscillating between, and the voltage being high means the LED is currently off, because now if we connect or push the button, the high voltage will turn it on. And then now that the voltage is low, we know the LED is on currently, because connecting the button will turn the LED off. And as you can push with this, and see the LED is on right now and the voltage is low on the oscilloscope.
So here we have an Electret microphone that is biased with this capacitor and resistor. The resistor allows the DC part of the circuit to power the microphone without the AC signal interfering with the rest of the circuit. This AC signal then goes through the coupling capacitor, which is right here, and to the DC part of the circuit, enabling us to properly use the microphone. So we can see when the circuit gets turned on, we can see the oscilloscope. And so when we play a 1 kilohertz tone, the oscilloscope reads the voltage from the microphone. Yeah, that's enough. That's good.
This is the op-amp section of our final project circuit. Here we have our power supply, and we use channels 2 and 3. Both channels were set to 9 volts and 0.5 amps. This first red cable of channel 2 corresponds to 9 volts. This is our positive VS. These 2 points correspond to our reference or ground, effectively 0 volts, and this black cable on the end for channel 3 is effectively negative 9 volts, and it's our negative VS, because compared to ground, since channel 3 is set to 9 volts, but this is 0 volts effectively, this is going to be negative 9 volts.
So we have a waveform generator connected as the input, and this generator provides a sinusoid wave with an amplitude of 100 millivolts, and that is the input, which goes to this part of the circuit, and that is measured by the oscilloscope, which shows the yellow channel and the green channel. The yellow channel corresponds to the input, which is getting amplified 10 times, and it becomes the green channel where we get 1 volt.
This is the integration of our microphone circuit and our amplifier circuit. Prior to their integration, when we spoke into the microphone, we could not observe significant variance in the voltage levels, but now that the amplifier is connected to the microphone, we can see that even talking from pretty far away changes how much variance there is in the voltage as displayed on the oscilloscope. This is the oscilloscope reading from our combined microphone and amplifier circuits for background noise. As you can see, it's a lot more stable than when we observed the clap, ranging from around positive 30 to negative 30 millivolts. This is the oscilloscope reading from our combined microphone and amplifier circuits right after a clap, and we can observe here that the oscilloscope readings go up from around 250 millivolts down to around negative 30, negative 40 millivolts.
So this is our final circuit setup for our final project, whereby this side will have the amplifier as well as the microphone. While this side will have the BJT latch. And we are not using the comparator because directly we will modify the amount we amplify instead of using a comparator. So how we integrate both sub-circuits is that this yellow wire gives the output of the amplifier into our MOSFET, which serves as the button in our BJT latch that connects the circuit together. So when we clap, the amplifier would give a peak voltage of about 1.3, which would then trigger and connect the MOSFET gate over here. And when we clap again, it will connect the MOSFET gate again, and it will turn off our LED light.
Go. 1.
And that's the clapper. Though this turned out to be the final product, we had a few additional ideas along the way. Like, what if we swapped the LED for an infrared emitter and added a detached infrared detector circuit that detects the infrared, turning on the LED from a distance? Or what if we got the circuit to oscillate by attaching a motor to it, continually turning the clapper on and off and on and off? However, in the end, due to time constraints, we didn't end up implementing any of these ideas, however fun and interesting they may be. In the end, ideas like these don't always make the final cut in engineering, not because they lack creativity or potential, but because engineering is as much about trade-offs, constraints, and feasibility as it is about innovation. And that may just be why something like the clapper would never work in the modern day.